Hello friends, today we have to start with another session on simulation, synthesis, flattening and resource sharing. Myself, Professor Nitin L. Ahire, MIT's Institute of Engineering, Nashik, that is lecture number 8 on simulation, synthesis, flattening and resource sharing. Simulation issues. We have started with simulation issues. First, simulation, then simulation process, delay modeling and types of simulation. Simulation. Simulation eliminates the time consuming need for constant physical prototyping. Simulation eliminates the time consuming need for constant physical prototyping. Simulation can be performed during all stages of verification. Simulation can be performed during all stages of verification. Motivation of simulation comes from the need to verify that the HDL code is correctly implementing the design. Motivation of simulation comes from the need to verify the HDL code is correctly implementing the design. Simply verify that the design meets its required specification. Simply verify that the design meets its required specification. Simulation. The simulation eliminates the time consuming need for constant physical prototyping. Simulation can be performed during all stages of verification. Motivation of simulation comes from the need to verify that the HDL code is correctly implementing the design. Simply verify that the design meets its required specification. Flavors of simulation. Flavors of simulation. Functional simulation. Functional simulation is functional verification of the design without any delays. Is functional verification of the design without any delays. Then pre-layout simulation is functional verification of the design including logic cell delays. Is functional verification of the design including logic cell delays. Post layout simulation. It is performed after the physical place and routing. It is performed after the physical place and route, means interconnect delays are taken into account. Means the interconnect delays are taken into account. Flavors of the simulation, there should be having functional simulation, pre-layout simulation and post-layout simulations. Now the simulation at the different levels. Simulation at the different levels. So whenever it should be having in the module system, whenever it should be having in the module stage, then subsystem stage, means all the modules are combined together, so it is formed as subsystem. Now at the chip stage the simulation is to be performed, and now finally when the system can be made at the time of level, the simulation can be performed. So here we can show one long card, that is nothing but a complete system can be ready and then it could be simulated. So these are the stages or the different levels whenever we require to do the simulation. So modules, then subsystem, then chip level and then finally the system level. In this way, these are the 4 different levels whenever we have to perform the simulation operation. The comparison for simulation at module level and system level, subsystem and chip level. So first point we are taken into consideration, that is stimuli development. Whenever stimuli development is there at module side, it is difficult, but system side we go when it is easier. Then second parameter, that is simulation efficiency. Simulation efficiency at module side it is higher simulation efficiency, but as far as we moving towards from system side it is low simulation efficiency. Then nature of the detected problems, low level at module side, but as far as going towards system side it consider all kinds of detected problems. It considered all kind of detected problem. Then next, bug correction time. Bug correction time in module side it is low, but in system side it is higher. Then time in project, in module side it is early, but at the system side it is late. So this way we are doing the comparison in all the different levels, module, subsystem, chip and system, depending on the various parameters, that is stimuli development, simulation efficiency, nature of the detected problems, bug correction time and time in project. Now next, the steps which are included in simulation. The four main steps which are included in simulation, that is compilation, then elaboration, initialization and execution. Elaboration, initialization and the execution. These are the steps which are involved in simulation. So this should be the top down approach. First compilation, then elaboration, then initialization and then execution. So we discuss with these steps. First, compilation. The name itself it indicates that it will do the functionality of compilation. Means it checks the VHDL source code to check the syntax and semantic rules of VHDL. Compilation, it checks the VHDL source code to check the syntax and the semantic rules of VHDL. If a syntax or semantic error occurs, then the compiler flags off an error message. Here, if a syntax or semantic error occurs, then the compiler flags are of an error message. Next, else the compiler generates an intermediate code. Else the compiler generates an intermediate code. Semantics. Semantics means science of meaning. Semantics, science of meaning. And syntax, mechanism of language. Syntax, mechanism of language. Have you got compilation? It simply checks the VHDL source code to check the syntax and semantic rules of VHDL. If a syntax or semantic error occurs, then the compiler flags off an error message. Else the compiler generates an intermediate code. Semantics, it is science of meaning. Syntax, mechanism of language. Now steps in simulation, continuing. Next, elaboration. Elaboration. The ports are created for each instance of a component. The ports are created for each instance of a component. Memory storage is allocated for the required signal. Memory storage is allocated for the required signal. Interconnections among the port signals are specified. Interconnections among the port signals are specified. Mechanism is established for executing the VHDL process in proper sequence. Mechanism is established for executing the VHDL process in a proper sequence. Second, elaboration is there. Elaboration means ports are created for each instance of a component. Memory storage is allocated for the required signal. Then interconnections among the port signals are specified. Then mechanism is established for executing the VHDL process in a proper sequence. Third, initialization. Initialization, the word itself it indicates that it will do the initialization function. Initial values preset in the declaration. Initial values preset in the declaration statements are assigned to the signals and variable. Initialization means initial value preset in the declaration statement are assigned to the signals and variables. Then last execution. Every process is executed until it suspends. Signal values are updated only after this. Every process is executed until it suspends. Signal values are updated only after this. Simulator accepts simulation commands like run, assign, watch, which control the simulation of the system. Simulator accepts the simulation commands like run, assign, watch, which control the simulation of the system. Simulation ends when all the signals have been updated and new values have been assigned to the signals. Simulation ends when all the signals have been updated and new values have been assigned to the signals. Then the simulation process over there. Simulation process. Basic definitions for simulation process. Event. A change on component output that will be propagated. Component output that will be propagated. Event, a change on component output that will be propagated. Then transaction, a change on component input that does not propagate. Event. See that the difference in between event and transaction. Event means a change on component output that will be propagate, and transaction a change on component input that does not propagate. Another definition, scheduling. Future events generated by evaluation of a process. That is means scheduling. Now evaluation. Calculating the outputs of the components based on inputs and current state. Evaluation. Calculating the outputs of a components based on inputs and current state. Then agenda for synthesis. Here, what is synthesis? First, we have to go through what is synthesis. Then synthesis tools, expectations. Then synthesis tools, features, hardware modeling examples, good coding practices, and synthesis guidelines. Today's agenda on synthesis tools, expectations, features, hardware modeling examples, good coding practice, and synthesis guideline. So first we have to discuss about that. What is synthesis? What is mean by synthesis? Synthesis, the word itself it indicates that it will do the function of synthesis. Synthesis is an automatic process that converts user's hardware description into structural logic description. Synthesis is an automatic process that converts user's hardware description into structural logical description. When we use VHDL as a textual file, the process is called VHDL synthesis. When we use the VHDL as a textual file, the process is called as VHDL synthesis. Synthesis is a means of converting HDL into the real world hardware. HDL stands for hardware description language. Synthesis is a means of converting the HDL into real world hardware. Synthesis tools generates a gate level netlist for the target technology. Synthesis tools generate a gate level netlist for the target technology. Synthesis is equal to translation plus optimization. Synthesis is equal to translation plus optimization. So here we are having with that one more expression, that is x is equal to a and b or c and d. Here one more expression, that is x is equal to a and b or c and d. So here for that expressions we have drawn one structure. We are having with that 4 inputs, that is a, b, c and d. These are the 4 inputs. These 4 inputs are given to 2 AND gate as an input terminal. So a and b for one AND gate, c and d for another AND gate. So output of these AND gates are combined and given as an input to the OR gate. So here we get the value of a and b, and here we get the value of c and d. So finally at the x we get the output as x is equal to a and b or c and d. So for that here we are having with that the synthesis should be performed. So for that particularly we are combining one AND gate and OR gate and another AND gate, keep in separately. So the operation should be performed and it will be converted into one black box, that is lookup tables, LUT. So here these A, B, C, D, these signals are given to one of that lookup tables and it will do that functionality of whatever the functionality which we are combining these modules, that is AND and OR modules, that are combined, that all functions are combined together with this particular box. So it will give the result as an x is equal to a and b or c and d. So this particular synthesis is the process. It is target device technology specific. Synthesis is the target device technology specific, and synthesizer will try to use the best architectural resource available with the target. Synthesizer will try to use the best architectural resources available with the target. Now the several steps work out behind this particular scene. So first steps, translation, then the optimization, then mapping. So translation, that is nothing but hardware description which is written with hardware in mind. Translation, it is hardware description written with hardware in mind. Optimization, mix of boolean, other operations and memory elements. Mix of boolean and other operations and memory elements. Mapping means gate level technology to the specific techniques. Gate level technology to the specific techniques. Translation, translation means language synthesis. It design at higher level of description is compiled into known language element. It design into the higher level of description is compiled into known language elements. Optimization, algorithms are applied to make the design compact and fast. Optimization, the word itself it indicates that it will do the function of compact and fast, means design should be compact one and the faster one. So optimization, algorithms are applied to make the design compact and faster one. Then mapping, the design is mapped, means using architecture specific techniques. Design is mapped using architecture specific techniques, means gate level technology to specific one. Then here the design flow for synthesis process. Design flow for synthesis process. So here we are having with that HDL behavioral descriptions, then RTL synthesis and RTL optimizations. Already that terms we have know that hardware description, language behavioral descriptions, register transfer level synthesis and register transfer logic optimization, then high level description with Boolean equations. These are combined together with netlist, logic extraction and structured Boolean equation by logic optimization. So as far as concerned with that, logic optimization means it will simplify it or make the design compact one and faster one. Then structured Boolean equations can be formed. Then the structured Boolean equations can be formed, and these will be given to the technology mapping, means get level to the technology specific conversion, and after that it will be provided to the optimized netlist. These optimized netlist can be utilized to design a system. So in this way the design flow for synthesis process, same synthesis process which we will be discussed in unit number 3 also. So here in brief, synthesis process. Translation means inputs are transformed into a description based Boolean equation. Inputs are transformed into a description based Boolean equations. If the input data consists of get level netlist, then it is necessary to extract the Boolean equation to determine functionality of all used gates. Translation means inputs are transformed into a description based Boolean equations. If the input data consists of get level netlist, then it is necessary to extract the Boolean equation to determine functionality of all used gates. Technology independent logic optimization. This process aims to improve the structure of Boolean equations by applying rules of Boolean algebra. This removes the redundant logic and reduces the space requirement. Technology independent logic optimization. This process aims to improve the structure of Boolean equations by applying rules of Boolean algebra. This removes the redundant logic and reduces the space requirement. Technology mapping. This is the process of transforming the technology independent netlist into technology dependent one. Technology mapping. This is the process transforming the technology independent netlist into technology dependent one. During mapping, timing and area information of all usable gates of the target technology must be available. It is split into two phases. Flattening and the structuring. Synthesis process, translation, technology independent logic optimization, and technology mapping. In that, flattening and structuring is there. So first we will go towards flattening. Flattening means the aim is to generate Boolean equations for each output of module in such a way that the output value is a direct function of input. This equation reflects two-level logic in SOP form. The aim is to generate the Boolean equations for each output of module in such a way that the output value is a direct function of inputs, and these equations reflects two-level logic in SOP form. SOP, sum of product form. Resulting equations do not imply any structure. Good optimization results are obtained. Caution: in case of structured logic, this process would destroy the characteristic structure and its associated properties. In case of structured logic, this process would destroy the characteristic structure and its associated properties. Example, carry loop ahead adder. A carry loop ahead adder. Flattening cannot be applied to every logic circuit because the number of product terms may becomes very large. Flattening cannot be applied to the every logic circuit because the number of product terms may become very large. Structuring. New intermediate variables are inserted during the structuring process. Example, if A bar, B bar, C bar occurs 10 times, then the tool may get assigned X is equal to A bar dot B bar dot C and use X everywhere. Here, simple example, if A bar, B bar, C bar occurs 10 times in the tool, then it may assign to the x is equal to a bar, b bar, c bar, and it is used x as an everywhere. Finally, the subfunctions are substituted into original equations. Finally, the subfunctions are substituted into original functions. Compared to the logic before structuring, the resulting area is reduced. Compared to the logic function before structuring, the resulting area is reduced. Here, synthesis process review. Here is the diagram for synthesis process review. There should be having 3 inputs: design, constraint, in that area, and speed, and library is there, and 2 are the resultant netlist and report. So here translation process converts the RTL to a Boolean form. Translation process converts RTL to a Boolean form. Optimization is done on the converted Boolean equation. Optimization is done on the converted Boolean equation. Optimized logic is mapped to the technology library. Optimized logic is mapped to the technology library. Here, flattening is a process where all the design hierarchy is removed. Flattening is the process where all the design hierarchy is removed. The entire design is transformed into a flat generic SOP form. The entire design is transformed into a flat generic SOP form. Structuring is the opposite of flattening. It adds the structure to the generic design by extracting common logic factors and representing them as intermediate nodes to produce the compact logic. Structuring is the opposite of flattening. It adds the structure to the generic design by extracting common logic factors and representing them as intermediate nodes to produce the compact logic. Synthesis tool expectations. Synthesis tool expectation. A good synthesis tool should have perform the technology specific optimizations, that is vendor specific FPGAs and CPLD. A good synthesis tool should perform the technology specific optimizations, that is vendor specific FPGAs and CPLDs. It have best optimization technique. It have best optimization techniques. It allows the designer control. It have broad language coverage. It have broad language coverage. It allows the designer control. It provide user friendly debugging environment. It provide user friendly debugging environment. It have fast compile times. It provide clean and seamless link with backend tools. It provide clean and seamless link with backend tools. So synthesis tool expectation. A good synthesis tool should perform technology specific optimization, that is vendor specific FPGAs and CPLDs. It have best optimization techniques. It allows the designer control. It have broad language coverage. It provides the user friendly debugging environment. It have fast compile times. It provide clean and seamless link with backend tools. Synthesis tools features. Tool cost depends on feature provided by it. Tool cost depend on feature provided by it. Desirable features are replicating the logic, then duplicate flip-flops, remove unused logic, optimization across design hierarchy, resource sharing of adders, incrementers and multipliers, then automatic RAM inference. RAM logic is automatically mapped to the technology specific RAM cells. RAM logic is automatically mapped to the technology specific RAM cells. Synthesis tools features. Tool cost depends on feature provided by it. Desirable features are replicating the logic, duplicate flip-flops, remove unused logic, optimization across design hierarchy, resource sharing of adders, incrementers and multipliers, automatic RAM inference. RAM logic is automatically mapped to the technology specific RAM cells. In that first, replicating the logic. Here we have shown the diagram. Replicating the logic means here first one buffer is there, that will be driving the number of buffers. So that is nothing but call it as a fan out. So replicating logic to meet the fan out demands. Replicating logic to meet the fan out demands. Here example write may be connected to 100 points, hence add buffers to split internally. Then duplicating logic. We can duplicate the logic which generates the small for minimizing, which generates the signal for minimizing the fan out. We can duplicate the logic which generates the signal for minimizing the fan out. Trade-off. Loading effect of signals is reduced, hence lowering the propagation delay, but at the cost of logic and interconnect complexity. We can duplicate the logic which generates the signal for minimizing fan out. Trade-off means loading effect of signals is reduced, hence lowering propagation delay, but at the cost of logic and interconnect complexity. Here one D flip-flop is there and there should be having Q output is there. Total 8 outputs are there. So here we are duplicating that logic in D flip-flop again for 4 outputs and again D flip-flop for again 4 outputs. So here we are make the duplication of that logic. Resource sharing. The word itself it indicates that it will be sharing the resources. Some synthesis tools automatically perform a limited amount of resource sharing. For arithmetic expressions that are mutually exclusive. Some synthesis tools automatically perform a limited amount of resource sharing. So consider the code. Here we are having one code is there. Add select process select A, B, C, D. Begin if select is equal to 1, then y is equal to a plus b, else y is equal to c plus d. And if end process add select. Here we are having with that one functions, one if else statement is there. If my select input is 1, so I am performing the operation y is equal to a plus b. If not, then else y is equal to c plus d, and if end process. So for that, here understanding purpose we have drawn one diagram for resource sharing. Before the resource sharing, how it could be performed the operations. So a plus b, one of the operations, another operation c plus d. So here 4 signals are there. It will be combined through one of the adder circuitry is there, a plus b, and another adder circuitry combining the c plus d. So here you will get the a plus b and here you will get the c plus d. So these are the 2:1 multiplexer is there. So single select input is there. So out of these 2 lines, one of the lines will get connected towards the y terminal. So select is equal to 1, then a plus b will get targeted towards the y output. If select input is equal to 1, then a plus b get connected towards y, and if select input is equal to 0, then c plus d will get connected towards the y if my s is equal to 0. So in this way it will perform the operations of multiplexer. If s is equal to 1, so y is equal to a plus b, and if s is equal to 0, y is equal to c plus d. So before resource sharing it may perform the functionality like that, but after the resource sharing means the adder get share, and these are the 2 multiplexers. So here a and c is the input to the first multiplexer and b and d is the second multiplexer input terminal. So if my select is equal to 1, if my select is equal to 1 means if my s is equal to 1, so here a will be appeared and here b will get appeared, and y is equal to a plus b, because it will select line number 1. So a will get transmitted, b will get transmitted, so a plus b is there. Okay, got it the theory? Okay, so if another logic, if my s is equal to 0 means else function will be there, else case will be there. So here c will be there and here d will get appear. So y is equal to c plus d. So y is equal to c plus d. When s is equal to 0, so y is equal to c plus d. Got the idea? In this way, here we are sharing the adder resources in this manner. So an adder requires more floor space than a multiplexer. Then we are discussing about simulation versus synthesis. Some simulation constructs are not supported by synthesis tools. Some simulation constructs are not supported by synthesis tools. Example, wait statement. Synthesis tools ignore initial values. Synthesis tools ignore initial values. Care should be taken so that simulation synthesis mismatch does not occur. Care should be taken so that simulation and synthesis mismatch does not occur. Efficient coding practices. Efficient coding practices. Good coding style means that the synthesis tool can identify the construct within your code that it can easily map to the technology features. Good coding style means that the synthesis tool can identify the construct within your code that it can easily map to the technology feature. All programmable devices may have their unique architectural resources. Example, Xilinx Vertex series has built-in RAM. Coding for performance. Common mistakes is to ignore hardware and start the coding as it programming. To achieve the best performance, the designer must think about the hardware. To achieve the best performance, the designer must think about the hardware. Improve the performance by avoiding unnecessary priority structures in logic, optimizing logic for late arriving signals, structuring arithmetic for performance, avoiding area inefficient code, buffering high fan-out signals. Improves performance by avoiding unnecessary priority structures in logic, optimizing logic for late arriving signals, structuring the arithmetic for performance, avoiding area inefficient codes, buffering high fan-out signals. Efficient coding practices. It uses constants to enhance the readability and code maintenance. It uses constants to enhance readability and code maintenance. Comparison with a constant is preferred since it is much cheaper to implement. Since it is much cheaper to implement. Comparison with a constant is preferred since it is much cheaper to implement. To avoid the accidental latches, specify all clauses of if and case statement. Specify all clauses if and case statement. Specify all outputs. Use case rather than if then else whenever possible. Use case statement rather than if then else whenever possible. Use parentheses for better operation. Never use mode buffer. Again, use constant to enhance the readability and code maintenance. Comparison with a constant is preferred since it is much cheaper to implement. To avoid accidental latches, specify all clauses of if and case statement. Specify all outputs. Use case rather than if then else whenever it is possible. Use parentheses for better operation. Never use mode buffer. Design constraint. Constraining designs. Constraints are means of communicating our requirement to the synthesis and backend tools. Constraints are means of communicating our requirement to the synthesis and backend tools. Categories of constraints are timing constraint and layout constraint. Timing constraint and layout constraint. In timing constraint, maximum frequency is there, duty cycle, input delays and output delays. It avoids over constraining the design. Consequences of over constraining are design performance suffers, critical timing paths get the best placement and fastest routing option. As the number of critical paths increase, the ability to obtain the design performance objective decreases. Here, design performance suffers, critical timing paths get the best placement and fastest routing options. As the number of critical paths increases, the ability to obtain the design performance decreases. Runtime increases, runtimes increase. Then some synthesis guidelines. Simulate your design before synthesis. Simulate your design before synthesis. Avoid combinational loops in process. Avoid combinational loops in process. If a port is declared to be an integer data type, the range should be specified, else the synthesis tool will infer a 32-bit port. If a port is declared to be an integer data type, the range should be specified, else the synthesis tool will infer a 32-bit port. Avoid mixing clock edges. If a large number of both positive and negative edges flip-flops are required, then they should be placed in different modules. If a large number of both positive and negative clock edges flip-flops are required, then they should be placed in a different modules. So synthesis guidelines: simulate your design before synthesis. Avoid combinational loops in a process. If a port is declared to be an integer data type, the range should be specified, else the synthesis tool will infer a 32-bit port. Avoid mixing of clock edges, means if a large number of both positive and negative edge flip-flops are required, then they should be placed in different modules. Again, some guidelines. For best results, use technology primitives, means macros from the target technology libraries wherever possible. For best results, use technology primitives from the target technology libraries wherever possible. Try small designs on a target technology to find its limitation and strength. Try small designs on target technology to find its limitation and strength. Partition the design correctly. Eliminate glue logic at the top level. Partition block size based on the logic functions, CPU resources and memory. Separate random logic from structured logic. Separate timing sensitive modules from area sensitive ones. For best results, use technology primitives from the target technology libraries wherever possible. Try small designs on target technology to find its limitations and strengths. Partition the design correctly, means eliminate glue logic at the top level. Partition block size based on the logic functions, CPU resources and memory. Separate random logic from structured logic. Separate timing sensitive modules from area sensitive ones. Here unit number 1 should be unit number 1 to be concluded, and now tomorrow onwards we will moving towards the next unit number 2, digital design and issues. Unit number 2, digital design and issues. Thank you for the day.